So the next one we'll talk about here is hemispherical. So hemispherical emissivity. So hemispherical emissivity, you can kind of guess what this is going to be. So if I now take my emissivity and say integrate or get rid of any angular dependence, right, this is going to be the emissivity of the surface over the entire hemisphere, right? So let's write this out. So based on that, say based on emitted radiation over the entire hemisphere. All right, so we're kind of integrating over the entire angles there. So we would write this as let's see, epsilon sub lambda, right? So it's no longer epsilon lambda theta phi, it's just epsilon lambda. So epsilon lambda is going to be emitted radiation. So this is going to be now just units of watts per meter squared per micron. Right? No longer steradian because we've now kind of integrated that out, divided by the black body emitted radiation. And again, with units of watts per meter squared micron. Okay, let's draw kind of an example of this. So now if I have hemispherical emissivity, I'm no longer going to be considering the directional component, but I still do have that wavelength component. So what it might look like then if I plot out this epsilon lambda or define it in terms of the emitted power and the black body power, might look something like, okay, I've got a black body curve. Oops, I have a black body curve here, and that black body curve looks something like this. So this is going to be my E, capital E, B, lambda, my black body emitted power at a given wavelength. This axis being wavelength here in microns. And then this axis over here being emitted power. So if I were to draw for a real surface what my emitted power is as a function of wavelength, it might look, you just kind of make it up, but it might look something like, I don't know, something like this. Right, so I have some actual emitted power. So I could go in and measure my emitted power at each wavelength and then make this plot. Okay, this is now E sub lambda. So then what is emissivity as a function of wavelength? Well, it's just going to be, let's see if I can draw it on the same plot. So let's say over here on this axis, right, I'm going to go from, this is 1, this is 0. So I'm going to draw my emissivity as a function of wavelength on the same plot. So let's see, over here it's going to be kind of low. Right over here we have kind of a low emissivity. And then as we get over to this part, it kind of goes up. So let's say it looks something like, I don't know, like this. Right? You can kind of see that. So we start off with a low emissivity because the difference between these two should be drawn like this. So the difference between these two is pretty big, the ratio of those two. And then as you get to the right, it goes up. So that's the relationship between emissivity and emitting powers. Okay, so that's hemispherical. Let's talk then about I think the last one we want to define here, which is our total hemispherical emissivity. Okay, so total hemispherical emissivity, right? This is now, total implies all wavelengths, right? So all wavelengths, all angles, emissivity. This is the thing we're most familiar with from our previous use of the rate equations. Okay, so this would be, let's just write out the equation. So now it's just plain old epsilon, right? This is the one we're most used to. So this is emitted radiation in units of watts per meter squared, as opposed to watts per meter squared micron. It's just watts per meter squared now, divided by the equivalent for the black body. Again, with watts per meter squared. So this is going to be equal to what? It's going to be equal to capital E, our total emitted power, divided by E sub B, right? Which again is something we've seen before. So this is just our integral from 0 to infinity of E lambda d lambda over sigma t to the 4. Right, so there's our total hemispherical emissivity. And graphically, what this would be is, let's take our little plot here again. So we had our black body curve like this, and then we had our real surface curve like this. So all we're doing is we're just taking, right, the integral in this area and the integral in this area and taking the ratio of those two. Right, so this here, this is going to be this area. Oops, sorry. This sigma t to the 4 is this area. This up here is this. Okay, fairly straightforward concept, right? We're trying to define these terms, but now we have spectral directional emissivity. We have hemispherical emissivity, which includes wavelength. And then we have total hemispherical emissivity, which is just the integral of everything. All right, so just be careful about when we're talking about those different things, or what they all mean. All right, so yeah, I'll pause. Any questions or anything so far? Okay. So one thing that we often want to go from, say, this directional, spectral, or particularly spectral emissivity up to a total hemispherical emissivity. And we have to be a little bit careful about how we do that, right? It's not just, you can't just go up here and say, all right, my emissivity curve, this blue guy, I'm going to, let's say I want to estimate the total emissivity for this surface. I can't just take the average of it, right? Because what's happening here is, as you change your black body emitting temperature, right, that curve is shifting back and forth. That power as a function of at a given wavelength is moving, right? And so we can't just take the average, because where you are in relation to that emissivity curve is going to change based on your temperature. Right? So now, to go back and forth between these things, you have to account for the surface's temperature, the emitting spectrum. Let's think a little bit about how to do that. All right, so let's see. We start off with our definition of spectral emissivity, hemispherical emissivity, which is equal to E at a given lambda divided by EB at a given lambda. So let's see, what do we want to do here? So we can rewrite the definition we had before. Let's just write this in steps. So we have our integral from 0 to infinity of E lambda d lambda divided by sigma t to the 4th. What we want to do is define this in terms of our emissivity, like our spectral hemispherical emissivity. So we can do that by saying, okay, I'm going to integrate from 0 to infinity of my spectral hemispherical emissivity, epsilon lambda. Sorry, what did I put there? So this is, sorry, let me pause here. So I'm going to erase this part here. Be a little bit more careful what I'm doing here. So we're just rewriting this definition for emissivity. So now I'm going to write my total emissivity like this. So total emissivity, okay, is going to be this. It's going to be the integral from 0 to infinity of now my spectral hemispherical emissivity, epsilon lambda, times the black body, EB lambda, d lambda, divided by sigma t to the 4th, right? So you see all I did there was, I'm saying I can represent my E sub lambda, my emitted power at a given wavelength, by the product of the emissivity at that wavelength and the black body power, right? That's all I'm doing there. Okay, so we have this definition, but then, right, you notice that there is this temperature dependence in here. Right? There's, and so what we need to do is kind of look at how this might plot out. So let's do this. So here's my, let's see, here's my emissivity. Emissivity is a function of lambda from 0 to 1. And then on this axis, I have lambda. So let's say I have this emissivity curve and it looks something like this, right? So there's a pretty strong dependence of wavelength. Right? The point I'm trying to make here is the following. So if I look at an equivalent plot of emitted power as a function of wavelength, so emitted power here, this would be E lambda. So if I'm at a low temperature, right, my low temperature is going to have emitted power, say, down here. Right? So if I take that integral over from 0 to infinity and my emitted power is only down here in this region, what's the effective total hemispherical emissivity of this surface if it's at this temperature? Right? It's going to be pretty high. It's going to be up, say, in this region, because that's where I'm emitting power. If I am, however, at the temperature of the sun, right, and I'm doing something like this, now what's my surface's emissivity or absorptivity? Right? Well, it's going to be a lot lower, right? Because most of my power is interacting with the surface at a very low emissivity or absorptivity, right? So we just have to, you have to kind of be careful or cognizant of the fact that this thing, this relationship depends on temperature.